Welcome back everyone. We are now in the second part of lecture 2.6. We start with the definition of points of inflection, which are points where the concavity of the function changes. Formally, we say that the graph of f has a point of inflection or POI at the point P with coordinates CF of C if f is continuous at x equals C and the graph of f changes concavity at P. Take note that to be a point of inflection, f must be continuous first at that point. Equivalently, f has a POI at x equals C if there is an open interval AB containing C such that either one of the following happens. For number 1, f double prime is greater than 0 on the left of C and then f double prime is less than 0 on the right of C. That is, concave up on the left of C, concave down on the right of C. So there is a change in concavity. Well, for number 2, we have concave down on the left and then concave up on the right. Let us revisit our previous examples. We have f of x equals x cubed. We know that f double prime of x is 6x. And the table of signs, which we have already done a while ago, or our previous video, is the following. We note that f is continuous at x equals 0. And there is a change in concavity from negative to positive, concave down to concave up. Hence, the graph of f has a point of inflection at the point 0, 0, which is evident on the graph of x cubed. Now on to our second example, cube root of x, f double prime of x is this one. Our table of signs for this second derivative is the following. Again, we take note that f is continuous at 0. And there is a change again in signs or the concavity of our function. So concave up to concave down, and therefore the graph of f has a point of inflection at 0, 0. As we see in this graph of cube root of x. Okay? So before we move on, let's look at these examples and observe the following. For our first example, f has a POI at x equals 0. If we substitute x equals 0 on the second derivative, which is 6x, we have that f double prime of x, or of 0, is 0. On the other hand, cube root of x has a POI at x equals 0. If we substitute 0 on the second derivative, f double prime of 0 is undefined. Okay? This is actually always the case. That is, whenever a function has a POI at a point, then its second derivative at that point is either 0 or undefined. We present this in the next theorem. So again, if the point P with coordinates CF of C is a POI of the graph of the function f, then f double prime of z is equal to 0 or f double prime of c does not exist. As a remark or warning, the converse of this theorem is not true. That is, if f double prime of c is 0 or f double prime of c does not exist, f may or may not have a point of inflection at x equals c. Let us look at some examples where this happens. First, let us consider x to the fourth. It is easy to verify that its second derivative is 12x squared and f double prime at 0 is 0. But we notice on the graph of x to the fourth that there is no point of inflection at x equals 0. Concavity actually did not change. It's still concave up on the left of 0, concave up on the right of 0. So there is no point of inflection. Okay? For our next example, we have x raised to 2/3. F double prime of x is negative 2 all over 9x to the 4/3. And as we can verify that f double prime of 0 does not exist. But what if we look at the graph of x raised to 2/3, we see that there is no point of inflection at x equals 0. Why? Because on the left of 0, it is concave down. On the right of 0, it's still concave down. So there is no change in concavity. Okay? So again, if f double prime is 0 or undefined, it is not automatic that it is a point of inflection. But from these points where f double prime of 0 or undefined, we have now a pool of possible points of inflections for our function. So we summarize this on the following Venn diagram. So among all the points where f is continuous, a portion of that are points where f double prime of x is 0 or f double prime of x does not exist. And from these points, we have candidates. So not all of them are POI, but we have candidates for points of inflections to our function. Now to determine if indeed it is a POI, we need to check for the table of signs of f double prime and check if concavity changes at the point. Let us look at some examples. So we determine all the POI of our function and discuss the concavity of its graph. Our first function is x to the fourth plus 12x cubed. You can verify that the second derivative of this function is 12x squared plus 12x, which we can factor as 12x times x plus 1. F double prime is a polynomial, so it is always defined. Now, it is 0 when x equals 0 or when x equals negative 1. So, our possible points of inflection or PPOIs are 0 and negative 1. Our next step is to look at the table of signs of f double prime. So we look at the table of signs, we divide our intervals as follows. So divide by negative 1 and 0. Okay? We can plug in some specific values to determine the signs. So the left of negative 1, we can plug negative 2. So if x is negative 2, this is negative, so we have positive. Okay? Between negative 1 and 0, you can plug in negative 1/2. If x is negative 1/2, this is negative, and this is positive. So negative, positive, we have negative. Alright. And at the right of 0, we have, say, 1. This is positive, this is still positive. So therefore, at the right of 0, f double prime is positive. So we see here readily on this table of signs of f double prime that concavity changes. So from concave up, it becomes concave down. And then from concave down, it becomes concave up. Hence, there is a point of inflection at x equals negative 1 and 0. So we conclude as follows. Negative 1 and negative 1 and 0, 0 are points of inflections of the graph of f. So to see these points, we only need to substitute negative 1 and 0 at our original function. Okay? We also have the following conclusions. The graph of f is concave up on negative infinity and negative 1, and the interval 0 to infinity, and concave down on negative 1 to 0. Okay. So for our next example, we have the function x squared all over 9 minus x squared. Its second derivative is as follows. So from the second derivative, what is our possible points of inflection? The correct answer is, there is none. Okay? Why? Because you may say that it's undefined at plus or minus negative 3, but plus or minus negative 3 is not in the domain of f. Recall that to be a point of inflection, f must be first continuous at that point. But plus or minus 3 is not in the domain, therefore it's not continuous there. Okay? So from here, because there is no possible points of inflection, we readily conclude that the graph of the function has no point of inflection. But for the purpose of concavity, we still need to check for the table of signs of f double prime and include this plus or minus 3. Okay? So we have the table of signs, negative 3 and 3. We divide the interval. And then we check for the signs. Okay? Note that the numerator of f double prime is always positive. So we can only check, we only need to check the sign of our denominator. So we can plug in again values. Say the left of negative 3, negative 4. So if x is negative 4 here, this is negative. Okay? So we have negative. Between negative 3 and 3, so say x is 0, so 0, so positive. The right of 3, say x is 4, so if this is 4, it's negative. Okay? So from this, we conclude that it is concave down, so the function is concave down on the intervals negative infinity to negative 3 and 3 to positive infinity. And it is concave up on the interval negative 3 to 3. Alright, so let's move on to our third example. Our third example is the function negative x to the 4/3 plus 4x to the 1/3. Please verify that f double prime of x is this function, negative 4x plus 2 times x plus 2 all over 9x raised to 5/3. So f double prime of x is 0 whenever x is negative 2. On the other hand, it is undefined when x is 0. Hence, we have two possible points of inflection, negative 2 and 0. So we know the drill. Let's check for the table of signs for f double prime. We divide the interval for negative 2 and 0. And then we can plug in points. Okay, so say negative 3 for the left of negative 2. So if it's negative 3, x plus 2 is negative. We have negative here. 9x to the 5/3 is negative. So negative, negative, over negative, we still have negative. Okay? Now, between negative 2 and 0, say negative 1. So if it's negative 1, x plus 2 is positive. The one in the denominator is negative. Negative 4 is negative. So negative, positive, negative. So we have positive. And lastly, for the right of 0, say 1. So this is positive, but we have negative here. So we still have a negative value for f double prime. So with this table of signs, we readily can conclude a lot. So we have a point of inflection at x equals negative 2, because there is a change in signs from negative to positive. And also a point of inflection from at x equals 0. So we have concave up to concave down. So here are our conclusions. We have the points negative 2, 2 cube root of 2, and 0, 0 are points of inflections of the graph of f. And the graph of f is concave down on negative infinity to negative 2 and 0 to infinity, and concave up on the interval negative 2 to 0. Great. So this concludes this part of the lecture. On the next part, we will discuss the second derivative tests for relative extrema. That is, how we are going to use the second derivative to find whether a value x equals c is a relative extrema of a function. See you on the next video.